Well, good morning. Welcome to Calculus. We're going to continue our lesson with related rates, and we're going to drill down on this Roman numeral structure. So for Roman numeral 1, let's draw a diagram of a conical tank with vertex down. I don't know if you really want to design a swimming pool with this design. It's 10 feet across the top. Could be kind of dangerous. If you ever want to get really frustrated, fill a pool like this that's 12 feet deep with water, and then jump into it in such a way that your head gets wedged right in here. So, you'll be like, oh man, I feel like I'm stuck. How am I going to get out? That's for those who really have a craving for frustration. I want to do that. So, but that's not really the point of the problem. The point is to not be frustrated, but to instead solve a calculus problem. So, it's like the eyes are still there. So it's water's flowing into the tank. So let's draw a spout. This is a water spout. Water's flowing in to the tank. So let's draw the wavy surface of the water, because there's really two cones. There's the cone of water, and then there's the cone that represents the tank. And let's be cognizant of both of them. The cone that represents the tank has a radius of 5 feet. The cone of water has a variable radius. Would you please, instead of taking all the time to write the word let, like let R represent the radius of the water, I'm going to put an R here and an H. You see, the height of the tank is 12 feet, but the height of the cone of water is variable. So we're going to put the letter H there. There's two separate cones. And as you're getting to know this Roman numeral structure for related rates problems, can you begin to identify for me some of the things that are currently missing from Roman numeral 1, which is supposed to contain given information, variable definitions, and diagrams? What else needs to be added to Roman numeral 1? I'm taking your recommendations now. Dana?
The water's flowing at 10 cubic feet per minute.
That's given information. So can you give me a derivative?
DRDH? Or no, yeah.
Well, if the water's flowing into the tank, so that would require that we actually, that's a change in volume, 10 cubic feet per minute. Those are units per volume. So I should really put a let statement down here. What letter of the alphabet would you like to use to represent the volume, not of the tank, but the volume of the water? Yeah, so let V represent, you can't just say let V represent volume, that's not specific enough. Let V represent the volume of the water, not the volume of the tank, that's a constant. V is the volume of the water. And we also need to represent time with a letter. Let's let T represent time. So now I have the symbols that I can use to represent the 10 cubic feet per minute. What would be the calculus symbol used to represent 10 feet cubed per minute? Raise your hand if you think you know the calculus symbol that's equal to 10 cubic feet per minute. Marcus?
dRdt?
Yeah, dRdt is not correct because that would be the radius, or the rate at which the instantaneous rate of change in the radius. dVdt, and I had some students pushing back in their journal about, why do we have to say, or why can't we say over? Why can't we say dV over dt? I pulled up a Khan Academy video where they were teaching implicit differentiation, and Samuel Khan himself is pronouncing things like this as dVdt. Even Samuel Khan himself doesn't say over. There's some interesting things. He didn't use the word blob. Do you know what he uses instead of the word blob? A 2-syllable word, something. He says we have something to the squared power. It's 2 syllables. Why can't the guy just use the word blob? Maybe I'll have to type that into the comments section. Maybe I'll show you a clip from that at some point. But yeah, we use blob, it's 1 syllable, and students journal about the word blob in a favorable way. It's like you seem to enjoy using the word blob in math class. Here we have not dV over dt, it's dV dt is 10 cubic feet per minute. What else is required to complete Roman numeral 1? It's not done yet. Something missing. Ethan?
Isn't like a dxdt equals blank or something?
Yeah, well, in this case, it says find the rate of change in the depth of the water, so it's not dxdt.
d depth?
DHDT.
It's dHdt because the depth of the water is already defined, not with the let statement, but with a letter in the diagram. dHdt equals blank, question mark. And we want that to be evaluated at. So notice how I used the long vertical bar, the evaluated at bar, evaluated at h equals 8. So that's what we're looking for. Now, some variables are defined graphically. They've got to be one-dimensional variables, or things that show up in the diagram. Things like time cannot be represented graphically, so we define it verbally. And volume is not a one-dimensional, it's a three-dimensional variable. Things that are three-dimensional need to be defined verbally. Because I can't just put a V in the diagram and expect people to know what the V represents. Sometimes A for area can be represented without a let statement. You just put the A in the area, like the area of the rectangle. You need a let statement to define things like time, things that are difficult to see in a diagram. Time is hard to see in a diagram, and three-dimensional variables. Okay, so that's it for Roman numeral 1. Any questions on Roman numeral 1? There's a lot of work there, but it is important work for stacking the deck for success. Roman numeral 2 is one that really focuses your mind in the right direction. It's where you decide what relationship you're shooting for. Who thinks they know what letters go into the design of this relationship? And, it's unexpected. Sounds like the phone's off the hook. Okay, someone had their hand up. I think it's this. Here we go. Someone had their hand up. What are the letters that go in there, Jonathan?
V and H.
Yeah, we're piggybacking off, we're springboarding off of our work in Roman numeral 1. Yeah, it's going to be whatever, So, whatever those 2 letters are. In this case, it's V and H. Now, for the first time, we're going to get to use Roman numeral 4. In the past, we've skipped Roman numerals 4 and 5. This example is richer in that not only do we get to write the main equation, but also the related equations. Roman numeral 3, even though we didn't write it down before, the theme of Roman numeral 3 is the main relationship that's based on it's the main equation based on the relationship described in Roman numeral 2. I need some sort of equation. I either look in the back of the book to find a formula for volume of a cone, or if it's on the AP test, sometimes they'll give you the equation. Sometimes you have to create it on your own. Sometimes it's a brand new one that's never before been invented. In this case, there is a standard formula for the volume of a cone. It's V equals 1/3 pi r squared h. 1/3 times the area of the base times the height. So this is a reminder that a cone's volume is 1/3 the volume of the corresponding cylinder. Now, for the first time, we have a main equation in Roman numeral 3 that does not satisfy the goal that we've spelled out. Our goal here is to get an equation where the only variables are V and H. Those are what we call the desirable variables. We have, and this is awkward, we have an undesirable variable that's crept into the equation. So whenever you have an undesirable variable in Roman numeral 3, that's a signal that you need to come up with a Roman numeral 4 equation. Roman numeral 4 equations are relationships between desirable and undesirable variables. It's an important issue there. And I actually slow down the rate at which I talk for that because it's an important thing. So, I mean, it's very common for students in their math journals to give me feedback on not the instantaneous rate of change of volume with respect to time, but the instantaneous rate at which I talk with respect to time. It's like, come on, your dt, your rate of talking is too fast, slow it down. Well, this is a place where I'm willing to slow it down because we need to really focus on relationship between desirable H and undesirable R. Does anyone see a relationship, an equation that tells us how desirable H and undesirable R are related? Think CPSTP. CPSTP. It's a geometry thing, CPSTP. Some of you have taken geometry, or you know people who have taught geometry. Corresponding parts of similar triangles are proportional. You've heard of corresponding parts of congruent triangles are congruent, CPCTC, corresponding parts of congruent triangles are congruent. But you also learned in geometry that corresponding parts of similar triangles are proportional. And the Roman numeral 4 equation that you need here is based on similar triangles. And by similar triangles, I'm referring to this purple triangle right here, which is an R by H by hypotenuse triangle, and this red triangle, which I would argue is similar to the purple triangle. They're both right triangles. So angle-angle similarity. They both share a right triangle, or they're both right triangles, and they share this angle down here. So isn't the purple triangle similar to the red triangle by angle-angle similarity? Therefore, by CPSTP, corresponding parts of the similar triangles have to be proportional, which essentially means I can declare, using CPSTP, that in the purple triangle, the ratio of R to H has to be equal to the ratio of what to what in the red triangle?
5 to 12.
5 to 12 is correct. I want that to be in red. See if I can pull that off. 5 to 12 in red, R to H in blue. Now, this is the point at which MIGO tends to set in with a level of ferociousness that is very difficult to combat. If you want to avoid, and here you can see related rates problems, it's like there's letters, variables swimming all over the place. How do I make sense of this? Well, here's how you make sense of it, friends. And it's a phrase that I would commit to memory if I were you. I don't want you to memorize very much at all in calculus. But this is something that's worth memorizing. When you get to Roman numeral 4, this is the main equation, these are the related equations. And what I'm writing here in green, you don't have to show in your work just for vocabulary. The Roman numeral 3 is the main equation. Roman numeral 3 is main equation. Roman numeral 4 is related equations. Relationships between desirable and undesirable variables. We want to avoid MIGO, always solve the Roman numeral 4 equations for the undesirable variable. If I had known that one sentence, solve related equations for undesirable variables in the substitute of the main equation, then when I took calculus, I would have had many fewer episodes of MIGO, just bucketfuls of glaze scooped out of my eyes. If only I wouldn't have had to do that had I had this equation. When I say go, I'd like all of you to proclaim out loud and in unison this strategy statement. Solve related equations for undesirable variables. That's all. Ready? Go. Solve related equations for undesirable variables. Class, which variable is undesirable in this related equation? R. R is undesirable. So let's solve for R. Let's do that. This one sentence is the way to get inoculated from MIGO. We have 12R equals 5H, so R is 5/12H. Once you've solved your Roman numeral 4 equation for the undesirable variable, the undesirables are the variables that are not listed back in Roman numeral 2. Substitute that into the main equation to get V equals 1/3 pi times R, which is now known to be 5h over 12 squared times h. And upon simplification, we get upstairs 5 squared is 25. So we have 25 pi h cubed upstairs. Down below is 144 times 3. By the way, those of you who are interested in knowing what 144 times 3 is, it's believed by mathematicians to be 432. And this is the point at which you can celebrate. The celebration is required. You see, we set our goal in Roman numeral 2, and we had to do all this work. And sometimes the celebration can be as little as, woohoo, we were looking for a relationship between V and H, and we found it. Other times, when students reach their goal, they shout out things like, goal! Which is fun, you can do that too. The way to document that, we don't want you to actually scream during class, just write something like that. I've seen it all. I've seen boom shakalaka, or TWFP, Tiger Woods fist pump, or there's all sorts of different ways that people celebrate. So, and you're like, oh, Mr. Royce, are we gonna lose points if we don't celebrate? Are you really wound that tight? Can you see, if you're wound that tight, just unwind a little bit and celebrate when you reach your goal. Because you know what? When the celebration begins to die down, you got the celebration going up. Once it reaches a max, begins to die down, that's a signal that it's time to differentiate with respect to t. That's what Roman numeral 6 is all about. Roman numeral 5 is about sketching a graph of the celebrated equation. And the celebrated equation's graph is optional. Therefore, Roman numeral 5, which is the graph of V as a function of H, in this case, sketching that graph, completely optional. You don't have to do it. When the celebration begins to die down, that's a signal that it's time to go to Roman numeral 6, which is always to use the DDT operator. In fact, in that same video where Samuel Kahn uses the word something instead of much easier to pronounce word blob, he also refers to the derivative operator DDT. What you're going to do is you're going to differentiate both sides of the celebrated equation with respect to t. Class, would you please, in Roman numeral 6, do me a favor and show me what you think dv dt equals based on differentiating both sides of the celebrated equation with respect to t. I'm going to pause the camera while you try that. Ready? Go. Hey, we're back. Let's see if you know how to differentiate both sides of the celebrated equation with respect to t. I hope your Roman numeral 6 looks like dv dt equals 25 times 3 is 75 pi h squared dh dt, and 432 is part of the scalar that tags along for the ride. Raise your hand if you agree that dv dt is 75 pi h squared dh dt all over 432. Okay, it looks like about 40% of you agree with that. Any questions on how to get dv dt?
Yeah.
Keep in mind that 25 pi over 432 is a scalar multiple. It just comes out front. It's not affected at all by the differentiation process. Really, the only thing you're doing is taking the derivative of h cubed. The derivative of h cubed with respect to t is 3h squared dh dt. So as long as you understand that the derivative of h cubed is 3h squared dh dt, and then you're willing to multiply 3 times 25 to get 75, then you're in good shape. Are we okay then on finding Roman numeral 6? By the way, in case you're wondering where we're going, Roman numeral 1 tells us that we're aiming for dh dt. Well, we now have an equation that contains dh dt. I'm going to replace dv dt with 10. Solving for dh dt, it looks like the answer would be 10 times 432, or 4320, divided by 75 pi h squared. Of course, we could reduce that, but 4320, 75 pi h squared. That's basically the formula that I can evaluate DHDT, evaluate at h equals 8. So if you were to take the time to type all this into your calculator, 4320 over 75 pi times 8 squared is 64. That would be the answer. We better get the units right though. But change the depth of the water, that'd be feet per minute. So feet per minute, whatever this number is, feet per minute would be the rate at which it's growing. And by the way, if you're pouring water in at 10 cubic feet per minute, can you imagine that at first the water would be getting deeper pretty quickly, and then as time goes on, DHDT would get to be smaller and smaller. That makes sense because H is in the denominator. The bigger H is, the smaller DHDT becomes as time goes on. Yes, Derek?
So we're finding dVdt.
Yeah.
Why don't we find the derivative of the denominator?
Oh, well, wait a second. In V, the scalar multiple envelops the denominator. I mean, the denominator is part of the scalar multiple. So 25 pi over 432 is just, you can, I don't know what number that is. Maybe it's like, 0.3 or something. It basically comes out front and is not affected at all by the differentiation process. Further questions? Yeah, go ahead.
How did you get the 4320 for the numerator?
Well, in my head, I solved for DHDT, which involved replacing dVdt with 10, right? So I thought there's a number here, 10, and to solve for DHDT, I had to multiply both sides by 432, and 432 times 10 is 4320, and then divided by this. I mean, basically, to solve for DHDT, I have to multiply both sides by the denominator and divide both sides by the numerator. Yeah, go ahead.
Why isn't that cubic feet?
Why is what?
The label for the end. Why isn't it feet cubed?
No, well, height, it's a one-dimensional variable. Height is measured in feet.
Oh.
So the rate of change in height would be in feet per minute. The units would be feet per minute. Further questions? Yeah, there's a lot of details here. Now, instead of doing problem 6, for the sake of time, let's jump forward to the next page. And this is, 7 is parametric. Calculus AB does not do parametric equations. So yeah, we can get to one that's really a lot more interesting, the falling ladder. But this is a classic problem. If you have parents who have taken calculus, they probably remember trying to solve the falling ladder problem. This could be an opportunity to connect with the teenage or early college experience of your parents who have taken calculus. So let's take a look at this one. A ladder is 30 feet long. It's leaning against the wall of a house. And just to honor history, and this is what life was like for your parents. When your parents took calculus, teachers would write out problems using a technology we call pencil and paper. They would write out problems using handwriting, and then they would take them, these lesson plans to these things called Xerox machines. And the teachers would place the lesson plan on the Xerox machine and make copies, much like what you're experiencing here. This is a journey into what things were like way back in America in the 1900s. We're talking even 1960, 1970, 1980. This is what it was like back in for your parents in math class. So let's do Roman numerals 1, 2, 3, 4, 5, and 6. By the way, actually, I didn't talk about Roman numeral 8. That's where you write down the answer. We'll talk about that this time. So here we go. Roman numeral 1. Roman numeral 1. Let's draw a picture of a house. It has a ladder leaning next to it. House. In green, we have a 30-foot ladder. And someone thought it would be funny to pull a prank on the person who's on the ladder. They say, hey, let's pull the base of the ladder away from the house at a rate of 3 feet per second. You have to name, just like when Mr. Hockett was talking in chapel about Adam naming the animals, you get to name the numbers with either an actual number or a letter of the alphabet. So 30, the length of the ladder. Is that number constant or variable?
Constant.
It's constant, so we just write 30. We don't write L for length. If it's a number that stays the same, use the number. How about the base of the ladder? Let's call this the x-axis, that's the y-axis. How about the coordinates of this point where the 30-foot ladder hits the ground? Is that point constant or variable?
Variable.
Its location is variable. So what letters would you like to use to represent the coordinates of the point?
L0.
How about x comma 0? The y coordinate actually stays constant. The y is always 0, but x coordinate varies. We'll call it x. Now the y coordinate, basically where the top of the ladder is touching the house, the x coordinate stays at 0, and the y coordinate is variable. We'll call that y. So we're naming, everything gets a name. Children who are born get names. We don't want unnamed children running around the neighborhood. So, what else is needed in Roman numeral 1? It's not done yet.
Oh, the rates, like the given rates.
So tell me specifically, what can I write down to complete Roman numeral 1? Actually, see if you can do it. See if you can, on your own, complete Roman numeral 1. And then we'll see if you have it. Pausing the camera. Okay, I shrunk this down a little bit. Can someone tell me something that you put into Roman numeral 1 to round it out there? All right, Micah, what do you think belongs there? So we can just call that x. dx kind of means change in. The d essentially means the same thing as delta. It means change in x. So dx, what was the rest of that?
dt equals 3 feet per minute.
Yeah, 3 feet per second. 3 feet per second. And so how fast is the top of the, how can I represent this phrase? How fast is the top moving down? I need a mathematical symbol for that. So that's a change in y with respect to t. dy dt is unknown. I want to evaluate that when the base, so when, I want to evaluate that when x is w and when w is 8. So it's like there's w kind of crept in here. So you might be wondering, wait, should I call this w comma 0? No, you don't have to worry about that. I mean, you could, but when x is w is 8, when x equals w is 29. So that's what we're looking for. We need to define time, or define t as representing time. Let t represent time. Don't expect full credit unless every child has, every variable has a name. Okay, so I think we got that. Roman numeral 2. Relationship between, talk to me, class, what letters? I need a relationship between x and y. Who has one? Who has a relationship between x and y?
X squared plus y squared equals 30.
30 squared. So we'll call that 900. Yeah. Have we reached our goal yet, class?
Woohoo!
Control yourselves. Yeah. We have reached our goal. We have a relationship between x and y. There are no undesirable variables. So, Mr. Royce, can we use WH as our acronym for woohoo? Okay. If that's the way you want to be, I'll accept that. Go ahead to Roman numeral 6. Try Roman numeral 6 on your own.
Are we gonna have to like write out the Roman numerals?
Yeah, you do have to write the Roman numerals. I know that's asking a lot.
Like, if we don't write them, we're not gonna get full.
Yeah, because the directions will say use the Roman numeral format. So believe me, students thank me for this. It's like, oh, I thought the structure was going to be lame, but then they realize, oh yeah, I would have gotten Migo.
Wait, what does MIGO stand for?
M-E-G-O, my eyes glaze over.
Oh.
That's what happens when people are doing like related rates problems in calculus. It's like, they just stare at it. They think that somehow they'll finish the problem by staring at it. And then pretty soon, glaze forms. This is why. This is where Krispy Kreme gets their ingredients.
From MIGO?
From calculus students who don't use the Roman numeral method. It's like, oh, that's so disgusting. I hope you wrote 2x dx dt plus 2y dy dt equals 0. Raise your hand if that's what you wrote down for Roman numeral 6, 2x dx dt plus 2y dy dt equals 0. So you know, not only implicit differentiation, you also know the chain rule, and that's coming together to help you solve this important real-world problem. Because you might find yourself on a ladder someday in the vicinity of a prankster, and you need to be able to quickly, while you're falling through the air, while you're approaching free fall, you need to be able to calculate the rate at which you're going to be hitting the planet, returning to Earth. We always want those people who are way up there to return to the planet, no matter how high they go. Dividing both sides by 2, we've got x dx dt. Oh, you know what? This is actually a great time to replace dx dt with 3. So substituting on the fly, dividing both sides by 2 and replacing dx dt with 3, we've got 3x plus 2y times y prime equals 0. No, there's no 2 there because I divided 3 by 2. Doing a lot in my head. I don't like y prime there because y prime usually people think dy dx. I'm going to put back in the dy dt. Dy dt. So now, solving for dy dt, algebra 1 dictates that the answer is going to be negative 3x over y. Okay, now I've got to somehow evaluate dy dt when x is 8, which raises the question, when x is 8, what's y? Remember, it's a 10 Roman numeral method. Roman numeral 5 is optional. Roman numeral 10 is where you do scratch work. So for the first time, let's put the Roman numeral 10 in the 10 Roman numeral method. Roman numeral 10 is where you say, like, well, look, if I want to evaluate this at x equals w equals 8, I've got to figure out what is Pythagorean, a squared plus b squared equals c squared. What is the value of y in this Pythagorean thing when x is equal to 8? So in Roman numeral 10, we say, we do some scratch work. X squared plus y squared equals 900. So when x is 8, that's going to be 64 plus y squared equals 900. Subtracting 64 from both sides gives me 836. And the square root of 836, I'm just going to write it as the square root of 836. So now what I have to do is evaluate dy dt when x is 8 and y equals the principal square root of 836. So the answer to this problem is negative 3 times x is negative 24 over the square root of 836, and that's feet per second. Of course it's negative because dy dt, it's going down. Can you do the visuals on this? When your prankster former friend starts pulling this out, that's going to cause y to go down. You're going down. Question, Graham.
Where did you get the 3x?
Well, I probably did more than I should have in one step. First of all, I divided both sides by 2, so the 2's went away, right? And then, since dx dt is given as 3 feet per second, I replaced the dx dt with 3 to get 3x. Derek.
Are 7, 8, and 9 actual steps, or do we?
Okay, 7, Roman numeral 7 is going to be devoted to the first derivative test when we do optimization problems, which is not part of related rates. So you won't need Roman numeral 7 at all. Roman numeral 8 is where we write down the answer. So for VIII, for Roman numeral 8, we say that dy dt equals negative 24 over the square root of 836 feet per second. Roman numeral 8 is where you put your answer. And Roman numeral 9 is undefined. There is no Roman numeral 9. So it could be called the 9 Roman numeral method. But you might be wondering, well, why don't we just do our scratch work in Roman numeral 9? Well, the answer is that if we had Roman numeral 9 for scratch work, then you'd have to be doing this stuff like, wait, how do I make a 9 in Roman numerals? So I put the 1 here, there, and you spend half your time trying to remember how to make a Roman numeral 9. Yeah, it is over here for those of you interested. But no, it's not. Roman numeral 9 is undefined, so it's the 10 Roman numeral method, which really only has at most 9 possible Roman numerals, and you're not going to use 7 until a later section. So yeah, it's really streamlined because you have to use Roman numerals 1, 2, and 3. Sometimes you don't even need 4. 5 is optional. You need 6, and then put your answer in 8. Stephanie, go ahead.
In 8, you need to write out the answer verbally.
Basically in sentence form, yeah, because in word problems, it's mathematical etiquette, proper etiquette to answer it in sentence form. That's what Roman numeral 8 is.
Like the homework.
Right, yeah.
The answers.
Exactly. Marcus.
What's step 4?
4 is when you have undesirable variables in Roman numeral 3, like we did with V, R, and H. Roman numeral 4 is where you set up relationships between desirable and undesirable variables. We've had only one example that utilized Roman numeral 4, and that was right here, where we said, oh no, we have an undesirable variable. So we can't sell, we're inhibited, we're blocked from our celebration because of that R. R is not in the list. So Roman numeral 4 is where you set up mathematical relationships between desirable and undesirable variables and then solve those for the undesirable variable, okay? So that's the process. Now, I want to take a look at the extension to this one. There is something really interesting that happens here, that there's a tearing apart. Friends, it just rips. You can hear the rip of the model tearing away from reality. Because look at this. Look at what happened. Look at this thing. As x approaches, look at dy dt. As x gets closer and closer to 30, x can't get any bigger than 30. What's y approaching? It's approaching 0, friends. That means that the speed is approaching infinity. That means that according to this model, the rate at which you're falling surpasses the speed of light at some point, which means your mass surpasses the mass of planet Earth. Because once your mass gets right up there next to the speed of light, or your speed gets close to the speed of light, then your mass goes off towards infinity. So this is really quite the ingenious prank. By just saying, I'm just going to start moving the bottom of the ladder 3 feet per second, you're causing your friend, it's like, ha, now your mass surpasses that of Jupiter. No, that obviously doesn't really happen. I mean, yeah, sure, it's mean, borderline illegal to actually perform this prank. But your friend's mass is really not going to, I mean, because as you're falling through the air, assuming this is happening on Earth, you're going to hit a terminal velocity. Probably you're probably not going to end up going any more than 200 miles an hour because of the force of air, the wind resistance on you. So this model, although valid for values of x that are less than 30, once x gets close to 30, this model tears away from reality. And this happens, it's mathematical modeling. By the way, we didn't do it with w equals 29. It'd be super fast. If you'd have to go to Roman numeral 10. This was Roman numeral 10 with x equals 8. You'd have to go back to Roman numeral 10 again with x equals 29. See that 29 squared plus y squared equals 900 and solve that. So you get another answer. But let's go now to number 2. So here we are. In the 20 seconds that remain, let's set this one up. Now suppose we've got the 30-foot ladder again. No, now it's a 50-foot ladder. And the angle that it forms with the house, or does it say house or ground?
Wall.
Oh, with the wall. Okay, so this angle right here, theta. D theta dt is increasing, so it's 1/4. So, even though, tomorrow, so quiz, I think it says quiz on the syllabus. We'll finish this problem before we take the quiz tomorrow. The homework is on the syllabus. Well, check the syllabus to see when the quizzes are coming.
Quiz on Tuesday and then test on Thursday.
Yeah, right. So quiz is tomorrow, and then test on Thursday.
Will we get the quiz?
I feel like
And then I'll give you the quiz back to go over before the test. Both of the quizzes you're getting before the test. All right, have a good one. You.